Right. So I believe today is when I'm supposed to start reviewing mechanical concepts. So you guys are going to learn like kind of sort of statics from an EE professor. So it's going to be a fun time. Um, so the first thing that we're going to talk about today, let me just write this down. Review of mechanical concepts. So the first thing that we're going to talk about is stress and strain. Okay. So let's define stress as the intensity of internal forces within a body due to loading. So in a MEMS device, there are typically two types of stresses that we will observe. They will be a normal stress and a shear stress. So I want us to start by looking at normal stress. And to do this, I'm going to draw kind of a diagram here. Okay. So just drawing a three-axis system real quick like. So let's say that this direction out of the page is Y, this direction is X, and our vertical direction is Z, like so. And I'm going to attempt to draw a structure here. I want that to be a different color. So something akin to this. Okay. And we're going to say that we have, sorry, some force acting on this structure, specifically in the X direction, like so. Okay. I'm going to define a few of the parameters of the structure as well. So let's say that this dimension, so its length in the X direction will be lowercase l. Its length in the Z direction will be lowercase h, and its length in the Y direction will be lowercase w, like so. And we're going to say that the vector area that is representing this system is in the X direction. So we're talking about that cross section of the box right there. So let's say that the average normal stress is the magnitude of the applied force over a transverse cross-sectional area. Or mathematically, T subscript XX will be equal to the force in the x direction divided by the vector area in the x direction. Now, I am using the letter T to represent stress, where most mechanical engineering textbooks and stuff like that are going to use sigma, because as an electrical engineer, sigma represents electrical conductivity, and that is also something that we're going to be talking about in this class sometime in the same problem. So I'm going to have to get kind of fast and loose with symbols and stuff in this class, okay? So I'm just going to make a note here. Capital T will be the symbol or stress in this class. Okay. So I have defined a mathematical relationship for the average normal stress because that's the thing that we're going to principally be concerned with. The actual normal stress at any point is likely going to be different than the average, but average is where we're going to leave things at. So I just want to make that clear. Okay. So we have our beam box, whatever you want to call it here, loaded with a force acting along that cross-sectional area A there, pulling out this way, okay? To contrast that, I want to talk now about shearing stress, which is going to require another picture. So give me a moment to come up with that real quick. Don't want to be mean and just copy paste because that pisses you guys off. So same basic directions, X, Y, and Z. Hopefully a relatively same basic box. So same dimensions, I'm not going to bother writing those down again. And let's say that this time, our force is kind of pulling on this top surface. So here's our force directed in the X direction again. This is the cross-sectional area that we're going to be dealing with. Its vector direction is in the Z direction, so orthogonal to that plane. And we are going to define a average shearing stress as the magnitude of the applied force to an in-plane cross-sectional area. or mathematically in this case, Tzx will be our force f of x over our vector area a sub z. The shearing stress is not uniformly distributed over the area that the force is applied to. We'll get into that in a little bit more detail in a bit. Okay. So here is the different type of stresses that we are going to see. We are either pulling on a whole surface area or applying a force along the edge of the device. Either way is going to cause some form of deformation. So now that we're going to be talking about deformations, let's define strain. So let's say that the strain in a system is the intensity of deformations caused by mechanical stress. Okay. And so we're going to talk about normal stresses, or excuse me, normal strains, and then shearing strains. Okay. So if we go back to our normal stress diagram here really quickly, if we apply this force in the x direction, what should we expect to happen? Okay, so like what kind of deformation might we expect to see? Anybody have any thoughts? So if I pull on an elastic body in the x direction, what's going to happen to it? It's going to get longer in the x direction. Okay. Is anything else going to happen? It's going to shrink in the z and the y directions. Okay. So under a normal stress, a beam will experience deformation in the x, y, and z directions. So again, drawing a shitty little picture here. Okay. At least this one's only going to be 2D, so hopefully I can manage to not screw this up too bad. So let's say that this is our z direction, this is our x direction, and I'm going to try to represent the y direction as coming out of the page as a head of the arrow directed out like so. Okay. And this box will represent actually, let me do it this way. The beam prior to deformation. Okay, so something akin to this. And I'm just going to put a note out here. Dash is before deformation. And this original length here is our length L. And this original height here is our height H. So after we pull on this thing in the x direction, what we're going to see is something that looks like this. Obviously, rather exaggerated. So here's our force acting in this direction. And we've seen that the length of our beam has increased by some factor delta L, and the height of our beam has changed by some factor delta H. Okay. So we're going to say, actually, let me do this. Solid line is after deformation, just so we can all make sure that we're catching. We're going to define a longitudinal strain as the relative change in length due to an applied stress. And mathematically, this will look like S subscript XX will be delta L over L. Okay. And just for the hell of it, I'm going to make a note here that says S will be the symbol or strain in this class. Okay. And we're also going to experience some form of transverse strain, which I will illustrate with yet another picture. So here's our Z direction yet again, but we're looking at it from a slightly different way. So this is going to be our Y direction, and X will be directed out of the page. So prior to deformation, we have something like this. And as we pull it out of the plane of the page, we're going to see that it'll shrink in both the Y and Z directions. So something like this, where I'm assuming it's kind of anchored to the origin. So if, damn it. This was our original width in the Y direction, and this was our original height in the Z direction, then this amount right here is the change in the height, and this amount right here is the change in the width. So that our transverse strain is the relative change in the lateral dimensions of a body due to an applied stress. And we'll see two here. So one in the Y direction, that will be the change in width over width, and one in the Z direction, that will be the change in height over the original height. Okay. And in this particular situation, we should expect to see that the transverse strains SYY and SZZ should be approximately equal to each other. Okay. So why, if we increase the length of our beam, does the cross-sectional area of our beam essentially need to decrease? Well, because the mass of the beam has to remain constant, right? So if the mass of the beam has to remain constant, and the density of the material is a material constant, then the only thing that can change is then the volume, right? And so if we increase the length, then the height and the width need to go down in order to keep that overall mass of the system as a constant, okay? So this relationship is mathematically described by what's called Poisson's ratio, okay? So Poisson's ratio, Poisson ratio, says that nu, so that's the Greek letter nu, looks like a V, is going to be negative SYY over SXX needs to be equal to negative SZZ over SXX if we apply a force in the X direction. So I think we have a relatively good grasp of what's going on with normal strain. So now let's talk about shearing strain. Okay. So let me go up here. So shearing strain is measures the change in the shape of a body undergoing deformation. So when we had our normal strain, right, our rectangular cross-section beam still looked like a rectangular cross-section beam. Well, if we apply some amount of shearing stress to our system, we're going to cause that beam to mechanically deform, and its cross-sectional area is going to change significantly, right? So a very exaggerated look at this might be something like this, right? So establishing my coordinate system again. Here's my Z direction, my X direction, Y will be directed out of the page. Here's what I'm starting with. And here's something I might end up with. I need to draw that out longer. Maybe something like that, where my force was applied up here. And again, I'm assuming that my body was anchored at the origin, so where that part can't move. Okay. So this distance from here to here was our height. And this distance from here to here was our change in X. And we're going to define our shearing strain mathematically. Sorry, SZX as the change in X divided by our height. Another way to think about this shearing strain is that it's representing some amount of rotational displacement that's trying to occur here while we keep this thing anchored in one place, right? So if we push on the outer surface, only it's going to change if our bottom surface is locked into place. So stress and strain are related to each other. By a constant called the modulus. Oh, actually, don't close those parentheses yet. Of elasticity. Under small deformations, stress and strain are linearly proportional. So we might have the relationship, sorry, that should be a T, not an I. Txx is equal to E times Sxx, where this guy E right here is Young's modulus of elasticity, typically measured in gigapascals, and it is a material constant that quantifies the stiffness of a material. And then we can also have a relationship that Tzx, our shearing stress, is going to be equal to G times SZX, our shearing strain, where this G is going to be the shearing modulus typically expressed in newtons per meter squared, which quantifies the ductility of the material. And these two constants are related to each other through Poisson's ratio. So we could say that G, our shearing modulus, is going to be equal to E, our Young's modulus, divided by 2 times 1 plus Poisson's ratio. Now I'm going to attempt to draw yet another shitty graph, so I'll pre-apologize for this, to try to show how these guys are related to each other for an elastic material. Okay. So on this axis, I'm going to put strain, and on this axis, I'm going to put stress. And now I'm going to try to draw this shitty picture, and then I'll talk my way through what these regions and things like that are. Okay. So I'm going to start off with a region where things are looking pretty linear, if I were capable of drawing a straight line. Then we're going to see some changes like so. I'm going to put this X point right here, where this represents the fracture point, or our material can no longer deform and it literally breaks. Okay. So let me annotate this guy a little bit further. So I'm going to say that this point right here, where I stopped trying to make the line straight, this is going to be representative of our proportional limit. Right. So up until this point, stress and strain are linearly related. As we go beyond this point, we're going to hit our yield stress. And then I'll annotate this further. So after we go past our proportional limit, we have entered the plastic regime. So I'm going to let's denote these things here. So this is going to be region 1. I'm going to talk about it here in a moment. This is going to be region 2. Up to this point is going to be region 3. And lastly, over here on the other side of the region 3, we have region 4. Okay. So region 1 is the elastic region. Where stress and strain are linearly related. And I'm using the indices I and J here as kind of dummy indices for the directions that we're interested in. Okay. So in this region, if the stress or the applied force is removed, the material should return to its original shape. And this force loading can be repeated over and over and over again without causing any sort of permanent material deformation. Okay. Region 2, actually, let me note here. Does not permanently deform. Region 2 is the perfect plasticity region. Stress and strain are no longer linear related. Oops. That just looks like 2 J's. Okay. And plastic deformation has occurred. Region 3 is the stress hardening region. where the stress increases as the material elongates until the ultimate strength point is reached. Which would be this point right here. So the maximum amount of stress that we can get. And then we'll see that beyond this point is the necking region. And in the necking region, essentially the cross-sectional area of the material starts getting smaller very rapidly. Decreases until fracture occurs. Yep. Necking? Yeah, Necking. It might be useful, and I feel like this probably was covered in statics, but I can find a Google image just real quick, like for this to kind of help you understand why it's called that. Let me go back to this thing real quick. Let's see. Yeah. So this is a pretty simple thing. If you guys got to play with the equipment in the statics room while you're doing stuff, right? So you're pulling on this material from both directions, pulling, pulling, and pulling. Under the normal mechanical deformation or the like in the plastic regime and all of that kind of stuff, like this is going to keep this cross section, but you get to a certain point to where you've caused so much deformation that the cross-sectional area in this region is getting smaller and smaller and smaller. And it's effectively a positive feedback loop where that it's going to continue to decrease rapidly until it literally can't sustain it anymore, at which point it just breaks. So you're elongating this section, and that's what they call necking. Okay. All right. So in this class, we're going to be dealing mostly with semiconductor materials as our substrate, okay? Now, a semiconductor material is a very brittle material. So its stress-strain relationship is going to look actually significantly different from something like a metal, which is what this is more in tune with, right? So for a semiconductor, we're going to see something like this. So once again, strain on our x-axis, stress on our y-axis. Did I make that curve blue before? I did. So here we've got all our linear region. Then we're starting to get into the plastic region and it snaps. So this is what the stress strain relationship looks like for silicon, and most other semiconductor materials are going to behave pretty much like this, right? So they can't withstand a crazy amount of deformation. They're just going to break. We're still going to use them as beams and springs and all of that kind of good stuff, as we'll see here in a minute. But essentially, we should not expect large amounts of deformation or anything. Okay. Which is why it's great for micro scale stuff when the deformations that we're looking for are on the order of a few microns. So just for what it's worth here, I'm going to make a little table for you guys as well. And I believe I include this when it's necessary in the homework assignments and stuff. Um, so in this leftmost column is going to be our material. So I'm going to put SCSI. So this stands for single crystal silicon. Specifically, when we're looking at the 100 material plane. So that's going to have a Young's modulus measured in gigapascals of 130 gigapascals, and it will have a Poisson's ratio of about 0.25. If we're looking at the 110 family of planes of crystal silicon as our surface material, it has a Young's modulus of 170 gigapascals, Poisson's ratio of 0.30. The 111 family of planes is got a Young's modulus of 189 gigapascal, 0.36 Poisson's ratio. And then lastly, if we're looking at polycrystalline silicon, so I'm just going to put poly SI, we have 160 gigapascals for Young's modulus and 0.25 as our Poisson's ratio. Okay. So I mentioned a moment ago that we're going to be using semiconductor beams as springs. So that makes me want to talk about all that kind of good stuff. Okay. So the reason why we have to use beams as springs when we're dealing with MEMS devices. So when you think of a spring, let's start there. What do you think of? A coil. Yeah. So a coil of some metal or something like that, possibly a plastic if you've got a slinky or something. But anyway, it's a coil, right? Coiled up, long, deforms, all of that kind of good stuff. We can't really do that with semiconductor materials because it's really, really hard to process a coil like that. So instead, we rely on beams to act as springs in our systems. So we're just going to have beams that will act as the suspension, sometimes the mass, all of that kind of stuff as well. But they will be allowed to extend or bend in various directions, and we need to understand how that works. Okay? So now we're going to talk about beams as springs. So we're going to start off with the most simple shape, and this is going to be the extension rod spring. So defining my coordinate system, here's my Z direction, here's my X direction, and this surface over here, this plane, is going to be the anchor point of my system, right? So here's my original beam. If I apply a force in the X direction such that this beam is undergoing normal stress, what I should see is that this guy's going to get longer, right? So after I apply my force, it should look something like this, where I'm kind of fudging the fact that it's also going to get skinnier just to make this easier to illustrate, right? So here is my, nope, I want that to be a different color. Force in the X direction. Here's my cross-sectional area in the X direction. This is my original length. And then that's my change in length for this system. Okay. So this is an extension rod spring undergoing normal stress. And we could find that our stress is simply Young's modulus times our strain. Right? Nothing going on too crazy here. And so, since my average normal stress is defined as the ratio of my force over my cross-sectional area, this is going to be equal to Young's modulus times my strain. Well, my strain is defined as the relative change in length of my beam. So that'll be delta L over L, like so. Okay. So what I'm going to do really quickly here is I'm just going to algebraically manipulate this thing. Okay. So I'm going to say that my force is equal to Young's modulus times my area times my change in length over my length. And the reason why I've written it this way is because if I'm treating this rod as a spring, I want to make this look as close to Hooke's law as I can. How many of you guys remember what Hooke's law is for springs?
Okay.
Yeah, F is equal to Kx. So F is equal to, force is equal to the spring constant times the displacement. Well, the displacement in this case is the delta L, okay? So if I say that this is equal to K sub E, the spring constant for an extension rod, times delta L, then I can say that my spring constant in this system, K sub E, is just E A over L. Okay. So that's going to tell me how stiff my spring is, dependent on the material by Young's modulus and its geometry, cross-sectional area, as well as length. Okay. So in order for us to get a large displacement out of an extension rod spring, okay, we need it to be a relatively soft spring. So that means that it needs to have either a really long length or a really small cross-sectional area, right? So like I said, this is the most simplest one to figure out. So feel like we probably got this one. I'm going to move on to one that's a little bit more complicated, okay? So the next one that I want to talk about is a cantilever beam. Once again, establishing my coordinate system. Oh, and let's see, anchors over here, Z direction, X direction. So dash line represents my original system before I apply a force. And what I'm going to do, I'm going to erase this in just a moment, but I want to be clear that we're all understanding what I'm doing. I'm going to be applying a force in this direction. So a force in the Z direction. And so when I applied the force in the X direction, it extended in the X direction. Now, if I apply a force in the Z direction, particularly in the negative Z direction, we should see that this beam bends or deflects downward, right? So it should look something like this after. Yes.
Area, the height of the beam is not smaller. It's gonna stay the same, it's just gonna bend.
Yeah. So I'm going to draw some axes here along this guy so that we can kind of figure out what's going on. So this guy is supposed to be directly in the center of the original beam. And this guy right here is in the center of the deflected beam. So this distance right here is the amount of deflection that we have experienced. Okay. And then we can also define, so if I draw a line extending out of this, so perpendicular to that surface, we can define some angle, theta, that tells us the angle of deflection as well. Okay. Now, unfortunately for us, this kind of movement isn't nearly as easy to mathematically model. Okay. So we're going to have a differential equation that governs our beam displacement in this case. So that's going to be EI times the derivative of Z as a function of position with respect to x squared. And this is going to be equal to m of x, where m of x is the bending moment. Let me write this out here. Bending moment at location x, and this I is the second moment of inertia. Okay. In the direction of beam bending. So since we're dealing with a beam as a spring, and we're going to assume that all of our beams have rectangular cross sections because that's the easiest shape for us to make, they're all going to have the same second moment of inertia. So I can just replace I with the expression I is equal to AB cubed over 12, which is just from my good old handy dandy statics textbook from 20 years ago at this point, where B is the direction of beam bending. And A is the direction of transverse cross-sectional area. So just to be clear that this is making sense to everybody here, let me define a couple of things really quickly, right? So this was our original length. Okay. This dimension in the z direction was our original height, and then its width directed into the page, right? Or W would be into the page. So H is the dimension in the direction of beam bending, right? So it's its height in the z direction. So in this case, B would simply be H, A would be W. Okay. So if we assume the boundary conditions at the fixed end where x is equal to 0, R0, meaning that z at 0, sorry, is equal to 0, and we assume that the derivative at 0 is also 0. So this means that the beam cannot move or rotate. Um, then the second order equation can be solved by using integration. So starting with my differential equation, I've got EI second derivative of z with respect to position along the x direction. And this is going to be equal to my bending moment. So my bending moment here is going to be my applied force. So I should probably add that back to my diagram. So here's my applied force in the z direction. And then this is going to be L minus X, like so. So essentially, it's torque, force times length, right? So I'm causing bending. Okay. So I could divide both sides by EI and then take the integral of both sides with respect to X, leaving me behind with just Z on the left-hand side and math bullshit on the right-hand side. So that'll be force divided by EI, integral from 0 to where I'm interested in twice, because I had a second derivative, so I need to integrate twice, of L minus X. I'm using prime there as a dummy variable, like so. And if I integrate this thing twice with respect to X, what I'm going to wind up getting is F over EI times length times position squared over 2 minus position squared over 6. So this is telling me what amount of deflection I experience if my force is applied at some position X along the length of my beam. Okay. So maximum deflection is going to occur if I apply my force at the tip of the beam. Okay. So X would be equal to L. So I could say that Z max is just going to be F times L cubed over 3EI. And then I can rearrange this thing. Okay. So I'm going to put force hold on, sorry, I'm having trouble following my notes here. No, that's fine. So let's see. So F will be equal to 3EI Z max over L cubed. And this is my Hooke's law variation for this guy, right? So this is going to be K sub C, my cantilever beam spring constant, times my displacement, which in this case is Z max. And so we can see that the spring constant for a cantilever beam is going to be 3EI over L cubed. The angle of the beam with respect to rest position, theta, will be given by this relationship. So theta as a function of x is going to be the derivative of the tip displacement so that's going to be F over EI times LX minus X squared over 2. And the beam angle will be at its maximum. When X is equal to L, so the maximum angle occurs at the end of the beam. So theta max is going to be FL squared over twice EI. More things here. During cantilever bending, the top surface of the beam will be in tension and the bottom surface will be in compression. So something akin to this. So if I draw an axis along here, what I should see is that I've got kind of a profile like this. Of what's going on, right? Where I've got tensile stress that's trying to stretch the upper part of the beam and compressive stress that's contracting the lower part of the beam. The longitudinal stress bless you, at location Zx. So this is Z is equal to 0 is that axis of symmetry, right? So any positive Z means we're going up from there. Any negative Z means we're going down from there. And then X is obviously the length in the X direction along the length of the beam. So T at position ZX is negative MXZ over I. And since we know that our bending moment is just the torque, F is equal to L minus X, this is going to wind up coming out to be negative F of L minus X times Z over I. And from this expression, we can easily see that our maximum stress is going to occur when X is equal to 0, when we're at the anchor point of the beam, right? And the minimum stress, or 0, is going to occur when we're at the far free end of the beam. And so that's going to look like FLB over 2I, where again, B is the dimension in the direction of bending. Or we could write this as 3E B over twice L squared times Z, which is the amount of deflection that has occurred. All right, I think class is supposed to end in like 4 minutes. My hand's cramping up. I think I've bored you guys enough for today. So this will be a good stopping point. We'll start talking about guided beam and torsional springs in our next class meeting.
The only difference between the extension rod and the beams, difference in the direction of force.
Well, and the way that the beam is deforming as a result of the applied stress as well, right? So an extension rod is quite simply, you've got your thing connected to an anchor and you're just pulling on it. You're just trying to make it longer. Yeah. Whereas cantilever bending is going to occur when you apply a force in any direction that isn't just directly orthogonal to the surface of the beam, right? So if you want to have shitty bending, like it can have some component that is trying to extend it as well. But to get the largest possible deflection, you would want to apply it so orthogonal to that surface or orthogonal to the direction of extension. Thank you.